So I'd like to try and cover three topics. So just to give a general overview of the field of gravitational astronomy, and then look at how we actually detect signals in advanced LIGO data, and then from those detected signals, how we can pull out astrophysical information that's contained in the gravitational wave signals. Okay, so I'd start just by recapping what Brian was saying. So the field of gravitational wave astronomy sort of officially started, I guess, on the 14th of September last year when the two LIGO detectors observed the collision of two black holes, one 29 times the mass of the Sun and one 36 times the mass of the Sun, that formed a new black hole, 62 times the mass of the Sun, about 1.3 billion light years away. And all of that information we got from the gravitational wave signal that came from the last few orbits of the two black holes before they collided and merged to form a new black hole. And we saw a gravitational wave signal in the LIGO data in the sensitive band that was about 0.2 seconds long. So all of this astrophysical information was contained in this, few wiggles that we saw in the two LIGO detectors. And just to recap this very quickly, so what that signal actually was a strain in space-time. It was a physical distortion of space and time. So as the gravitational waves pass through the LIGO detectors, they're stretching and squashing the arms of the interferometers, and that creates a phase change in the laser light that we can measure. And this is something like a strain of about 10 to the minus 20 kilometers per kilometer. So we're looking at about change in the length of the arm to about 1,000th of a proton width over 4 kilometers. It's pretty amazing. I don't think I'll ever get tired of saying that. It's really cool. And there are lots of sources that we can actually measure at this kind of strain, and not just with LIGO. There are actually quite a lot of experiments that are devoted to finding gravitational wave signals. There's kind of a spectrum. And the range in frequencies is pretty huge. So right down at 10 to the minus 16 hertz, at super low frequencies, the gravitational waves associated with the Big Bang itself, so that the echoes of the Big Bang imprinted in the CMB. There are experiments like BICEP 2 that are looking for signatures of that in the CMB. As we go up further, higher in frequency at nanohertz, there are arrays of radio telescopes around the world that are looking for a stochastic background of gravitational waves. Those are associated with the mergers of the supermassive black holes at the center of all of the merging galaxies, and they should imprint this stochastic signal that by observing radio pulsars we can look for a stochastic gravitational wave signal there. As we move up in frequency to the audio band, so when people talk about listening to gravitational waves with LIGO, we're really looking for gravitational waves in the audio band frequencies between about a few tens of hertz up to a few kilohertz. And there are lots of cool astrophysical sources there. So some of the main astrophysical sources that we're looking for are the coalescence of compact binaries. So like the two black holes that we observed, maybe two neutron stars or a combination of neutron stars and black holes. And these are transient gravitational wave sources. They can be in the data for anywhere up to tens of minutes in the case of binary neutron stars, down to fractions of a second for the heaviest binary black hole signals. There are also continuous sources of gravitational waves that we can detect, such as pulsars, so spinning neutron stars with some kind of small deformation on them, so a mountain perhaps of the order of a meter. And these are constantly on. They're always in the data, but they're very weak signals, so you have to really look for a long time to be able to pull them out of the data. And then there's even more exotic things like the gravitational waves associated with supernova, so exploding stars, really bright, violent events. And these are all, when we talk about astronomy with LIGO, these are the things that we're targeting. So compact binaries, pulsars, and supernova. And there's a lot of rich science that we can do with it. It's kind of like 3 experiments in one, which is really neat: fundamental physics, astrophysics, and cosmology. So starting with physics, we're really testing fundamental properties of space-time when we see gravitational waves. So bear in mind that when we see a gravitational wave from something like the merger of two black holes, we're looking at, we're getting information about some of the most extreme environments in the whole universe. So when these two black holes collided, about 30 times the mass of the Sun collided at about half the speed of light. So the energy scales are enormous here. And the signatures we get are from just the most like extreme forms of space-time. You get objects made out of pure warp space-time colliding, and those signatures carry with them, information about that merger. We can also look at how matter behaves under extreme gravity. So if you consider an experiment like the Large Hadron Collider, for example, that's looking at hot nuclear matter, it's looking at sort of extreme temperatures, but not really extreme density. If we can observe gravitational waves from the merger of two neutron stars, we have a signature from an event that both has nuclear matter at huge densities, so that could contain information maybe about the equation of state of neutron stars, could tell us something important about nuclear matter. Maybe black holes have structure. So at least in general relativity, black holes are characterized just by their masses and spins. But there are sort of extensions of gravity and theories of quantum gravity where black holes have more to them than meets the eye. And by modeling these, we might be able to pull that out of LIGO data. In astrophysics, it's thought that maybe merging neutron stars, the trigger of gamma ray bursts, some of the brightest events in the universe. And then in cosmology, we want to be able to map the gravitational wave sky similar to electromagnetism. All right, so I want to just sort of change track a bit and look at how we actually detect gravitational wave sources. I want to look at two sources in particular. So transient sources, short-lived sources, and then continuous wave sources that are always on. And then finally look at how we actually extract astrophysical information and do inference on them once we make a detection. Okay, so the first step, compact binary coalescence. This is really one of the key sources of gravitational waves for advanced LIGO. So a compact binary is a binary system consisting of either two black holes, two neutron stars, or a neutron star and a black hole. And the idea is that this binary system forms, the two objects are orbiting one another, and gradually over time the orbit's shrinking. So the system's losing orbital energy, it's being radiated out in the form of gravitational waves, until eventually they become close enough that they merge and form a single compact object. And by the time these enter into the LIGO band, we could be seeing these transient sources from compact binary coalescence anywhere between tens of minutes, two neutron stars, to a few seconds or less for very heavy black holes. And these are good sources for LIGO for two reasons. One is that the sort of predicted merger rates are quite favorable. So from observations of binary pulsars and electromagnetic observations, we believe that we should see between a few to a few tens per year. They're also very well modeled. So over the last couple of decades, there's been a lot of effort in approximate analytic methods to try and describe binary coalescence, and also very detailed supercomputer simulations, so called numerical relativity, that simulate these events in great detail. And it's these simulations that allow us to, because we can simulate them so well, we can apply a match filtering technique to compare simulations of predicted simulations of events directly to the data. And these simulations form we can construct filter banks to just compare the data to the simulations. And this is shown quite nicely. So this, in this figure here that was taken from the detection paper. So the top panel is showing the actual signals that were observed on the left in the Hanford detector, and on the right in the Livingston detector. And below is our best fit supercomputer simulation that matches these well, that matches the signal at the top. And you can see, the signal was pretty strong. It was signal to noise ratio of about 24. And you can make out, the sort of chirping in spiral, and then the merger, and then you can see this ringing down here. And this is matched pretty well by our simulations. And then you get if you look at the residual of the simulation and the actual data, you see something that's pretty consistent with noise. And then at the bottom here is just a spectrogram. So the space of all of these possible signals that we can simulate is pretty big. It's a 15-dimensional parameter space. But in practice, we can limit ourselves just to a subset of all these possible signals. And these do a really good job of pulling out any kind of binary coalescence. Still on the topic of transient searches, there are also sort of more generic searches that are looking for not just compact binary coalescence, but other objects that perhaps aren't so well modeled as the compact binaries that I showed before. So I said that compact binaries were quite well modeled. That's almost true, but there are cases where they're not so well modeled. For example, if you have a very heavy very small black hole falling into a very heavy black hole. Other things that aren't so well modeled are like bursts of gravitational waves, so perhaps from supernova. So if this plot here at the top right, this is showing the gravitational wave strain from a supernova simulation. If you compare this to what you get from compact binary coalescence, it looks really chaotic. And it's because when you simulate a supernova, you're not just simulating gravitational fields, there's also nuclear matter in there. And there's also the stochastic processes. So the actual gravitational wave signals that get pulled out, they look kind of random. And one way you can actually try and search for these is just using a more generic set of filters. So say a sine Gaussian or a wavelet basis and some superposition of those to try and match these sort of more exotic looking signals. What's actually pretty cool is that you can use these to pull out these the signals associated with the first event. So you can sort of see the data. It's a little bit dim, but the blue and the red curves are these generic filters built up of wavelets that match the actual data pretty well. And if you compare that to the sort of expensive supercomputer simulations, they're actually, they look pretty good, pretty similar. Okay, so lastly, no talk about compact binaries or transients would be complete without talking about instrumental glitches. So glitches are transient events that occur somewhat more numerously than the actual astrophysical sources that we want to detect, and really a huge amount of effort goes into identifying and mitigating these sources by the operators of the instrument, and they have some fun sort of naming them. So you see the koi fish glitch, the raindrop, I don't know what Tomty is, Fringy the sea monster there. And these are associated with all kinds of things like trains passing by, laser light clipping the edges of the mirror, and general ghosts in the machine. But this would be a really big problem. But we have two detectors, and this is really the saving grace, is that glitches are uncorrelated usually between the two detectors. They occur randomly, whereas real astrophysical signals, they should occur coherently in the two detectors. So the gravitational wave signal hits one detector, a light travel time later it hits the other detector. And so you can mitigate these kind of sources, identify them, and then once they're pulled out of the data, we can look at the strain sensitivity to real gravitational wave signals, and this is taken from the detection paper just about the time of the event. And you can see this is frequency and strain noise, and you can see that we were sensitive down to about 10 to the minus 23, so these glitches here won't really do much of a problem, even though some of them look pretty similar to the chirping signals associated with transient events. So these are spectrograms, by the way, so time, frequency. Okay, so just still on the topic of detection. So continuous wave sources, these are sources that are always in a detector. And so maybe a prime source of these should be from pulsars, so rapidly spinning neutron stars. So you have a neutron star, and it's beaming out some electromagnetic radiation. And when the radiation passes through the Earth, you see a blip, radio, for example. And these are continuously emitting gravitational wave sources. An easy way to imagine how we actually detect these is to take examples of pulsars that are very well measured already from EM observations, so such as the Crab or the Vela pulsar. And we can use the EM data and just assume that the gravitational wave frequency is locked to the EM frequency. And if you take the Crab or Vela, where you know what the EM frequency is of the spinning pulsar, you can just look at a specific frequency band and just keep integrating the data in that frequency band over a long period of time to build up signal to noise ratio. With pulsars that are less well determined electromagnetically, such as CASIS or SCO-X1, and these are things where we know some of the orbital parameters, like we know where they are, but we don't know, say, how well the orbits are inclined, or the period derivatives as well. So there are a few extra search parameters there. And then there are searches for pulsar, like just any pulsar, so an all-sky blind search. And these these increasing computational costs, these are pretty expensive analyses. About half the LIGO computing budget goes to, is dedicated to searching for these sources. Actually, we have some volunteer computing to help out with this. So something called Einstein at Home, which you should Google, and if you're interested in searching for pulsars, you can sign up to this and dedicate some spare cycles. So similar to SETI at Home, but we're not looking for extraterrestrials. This plot here is just showing the sensitivity to pulsars during initial LIGO. So there's a lot of information, I don't want to go through it all, but there are three relevant things. So the green curve is showing a strain sensitivity during the science run in about 2010, 2011. And then some of these gold stars here are showing the upper limits of the gravitational wave strain associated with these targeted pulsar searches. And you can see that they're pretty much sitting on the noise curve, so we weren't able to very clearly see some of these pulsars. But if you look at this black curve here, that's the sensitivity curve for advanced LIGO during its design sensitivity, so what we should achieve in a few years. And if any of the gravitational wave strain from the pulsars lies somewhere between the green curve and the black curve, then we should be able to find the gravitational wave signals of some of these pulsars. And what's really cool about being able to do that is because the signals are always on, they're a pretty good test bed for testing theories of gravity. So gravitational waves, like electromagnetic waves, are thought to have two polarization states. But there are sort of more complex theories of gravity in which there are more polarizations. And these could be, they might be able to be uncovered from pulsar searches if the signals are loud enough. Okay, so the last thing I want to talk about is how we actually do some of the inference on these signals. I just want to look at the binary black hole case, because this is a very clean thing to simulate. This is the signal again, so this is time and frequency. And there's a hell of a lot of information contained in these signals. So remember, this only lasts for about 200 milliseconds. And we were able to tell where in the sky the black holes came from, how far away, how heavy they were. And this is the information that was shown in the detection paper. So when we quote sort of astrophysical parameter estimates, what we're quoting is what we're actually computing are Bayesian posterior probability density functions. And here it's showing the PDFs for the source masses. So this is the lighter source mass and then the heavier source mass, the distance to the source and its inclination. And you see the median value here peaks at about 29 for the lighter black hole, and about 36 for the heavier black hole. And these dotted lines here are the 90% credible intervals. And so these are reasonably well determined. I said that the distance is about 1.3 billion light years away. That's about 400 megaparsecs in astronomical units. And the reason that we're able to do this is there are two reasons. One is that the gravitational wave sources for binary black holes, the compact binary coalescence, it's very well modeled. So we have detailed supercomputer simulations. And we also know the statistics of the noise. So if you have some time series data that contains a gravitational wave, it's parameterized by some set of numbers like masses and spins of the black holes. And different combinations of these will lead to very different gravitational wave signals. So the signal here, this is from a simulation of two non-spinning black holes. The one on the right is a simulation of rapidly spinning binary black holes. And because we know the statistics of the noise quite well, we can build a likelihood function for the noise, compare the simulations, which are parameterized by things like masses and spins and the distance to the source and the sky location, and then build up a probability distribution of the signal parameters that parameterize the model and the signals. And we have a pretty neat toolbox to actually do this. So the kind of workhorse is Markov chain Monte Carlo that we use to stochastically sample the probability density function. Over the years, it's been enhanced with things like parallel tempering, kernel density estimation. You have very highly tuned jump proposals to explore the astrophysical parameter space. More recently, we've been developing sort of optimized model order reduction strategies to accelerate the computer and supercomputer simulations. To give you an idea, if you want to simulate a binary black hole system in numerical relativity, which is like the very detailed supercomputer simulations, they can take weeks or months to run the simulations. You're solving a set of like 15 coupled PDEs, simulating the curved space-time. And with these model order reduction strategies, which are employing things like a sparse representation of the signal space, similar to what we heard earlier, and high-dimensional interpolation, we can take that time down from weeks to months to something like tens of milliseconds or less. This really helps accelerate our inference and the simulation of the sources. We also have nested sampling codes if there are any sampling aficionados to do things like model selection. So this could be something very simple like, is the probability that the data contains a signal higher than the probability that it just contains noise? Or maybe we can ask more fun things like, is the signal described by general relativity or by some alternative theory of gravity? And this, I guess it's a common feature of inference is that these things are quite expensive. But we have reduced order modeling and ensemble sampling techniques are really helping to help us dig deeper into the data and pull out sort of interesting physical and astrophysical quantities. So looking forward, I think that it's no exaggeration to say that the era of gravitational wave astronomy has really just begun, and there's going to be a lot of exciting sort of cool science that's going to come out in the next few years, astrophysics and astronomy and fundamental physics. The detectors themselves, the advanced LIGO detectors, they're still not at their design sensitivity yet. It's going to be a few more years until we reach that sensitivity, and that's just going to increase our observational volume in the universe that we can reach out to. So we should be seeing more sources in the next few years than we have already. And as you were saying, like we have new detectors that are going to come online in the next few years in India and Japan. So I think I'll stop there and ask any questions. Thanks.